Welcome to this explainer on Texas Science Competency 004H. If you're a science educator, you know the daily struggle. How do you bring the absolute immensity of the natural world into a 40-minute class period without losing your mind or, let's face it, your students' attention? Well, today, we're breaking down exactly how scientific models make that happen. We're keeping things clear, structured, and highly focused on exactly what you need to know.
So let's jump right in with the crucial question. How do you safely teach a volcanic eruption? Or, for that matter, how do you teach something that's way too massive, like the solar system, or too fast, like the speed of light, or honestly just too dangerous to touch? You can't exactly bring molten magma into a middle school lab. The administration tends to frown on that. So you need a stand-in. You need a model.
To get there, our agenda for this explainer is pretty straightforward. 1. Making the invisible visible. 2. The Science Educator's Toolkit. 3. The Great Model Debate. And 4. Subject to change. Let's kick things off with Section 1, Making the Invisible Visible, or Teaching the Untouchable. Models are, without a doubt, the absolute backbone of science education, and they really serve 3 primary purposes. First up, they take these incredibly complex real-world processes and simplify them into a usable representation. Second, they give your students a literal sandbox for the prediction and testing of hypotheses. And third, they act as an essential tool for the communication of ideas and solutions. As this quote brilliantly illustrates, models serve as a shared language for explaining scientific ideas and design solutions. Think about it. When your diverse classroom with all its different learning styles is looking at the exact same physical or visual representation, you're stripping away all that tricky vocabulary confusion. You are building a collective, unified understanding. Moving right along to Section 2, the Science Educator's Toolkit, which is all about building that shared scientific language. All right, let's open up that toolkit. First up, we've got physical models. These are your hands-on, scale versions of objects. Like a plastic model of a plant cell where kids can physically point to the chloroplasts, a globe of the Earth sitting right there on your desk, or a model bridge constructed for an engineering challenge. These are absolutely fantastic for your tactile learners who really need to touch the science to grasp it. Next in the kit are conceptual models. We're talking mental or visual diagrams that show relationships. Whenever you draw a water cycle diagram on the board or map out a massive food web showing energy transfer, you're using a conceptual model. You are literally taking the invisible, abstract threads of nature and making them concrete for your students to see. And finally, we have mathematical models. This is where we bring in equations and data sets to represent phenomena. Honestly, mathematical models give your students a kind of scientific superpower, the ability to predict the future based on current data. Think of graphing population growth over a decade or running a complex computer simulation of a hurricane's weather pattern. Which brings us to the climax of our explainer with Section 3, the Great Model Debate, where we start pitting these models against each other. So here's an instructional approach I absolutely love, called the Great Model Debate. Instead of just handing a model to your students, have them actively argue its merits. Literally split the room. Have one side argue for the model's brilliant strengths, while the other side ruthlessly exposes its inherent limitations. Let's look at the actual arguments they're going to use. Okay, on the pro side of the debate, your students are going to argue visualization and safety. A great example, slicing open a styrofoam ball to reveal the Earth's hidden geosphere layers, or safely simulating a dangerous event, like that baking soda volcanic eruption, right at their lab stations without burning the school down. But then, the limitation side gets to fire back. Take a physical solar system model. If kids make the sun the size of a basketball, the Earth has to be the size of a tiny seed nearly 100 feet away. Models constantly force this compromise between accurate scale and proportion versus manageable complexity. Leaving out variables for simplicity is necessary, but kids need to learn how to spot that distortion. You really have to drive this home with them. Models are always a simplification. Because they intentionally leave out certain variables to focus on others, they result in less than perfect accuracy. A food web doesn't show every single microorganism in the soil, right? If it did, it would be pure chaos to read. Simplification is simultaneously a model's greatest strength and its most significant limitation. And don't forget to spark debate over the limitations of the materials themselves. The clay, paper, or plastic used for a classroom model behaves completely differently than real rock, water, or superheated plasma. Teaching students to articulate this reality gap between model materials and real materials, that is top-tier critical thinking.
Let's bring it home with Section 4, Subject to Change, exploring the tentative nature of science.
So to bring this all together into an actionable strategy, here is a 3-step process. Step 1, have them compare and contrast different models. Step 2, teach them to revise and refine. Throw some new evidence at them midway through a lab and force them to update their model to reflect it. It perfectly illustrates how science is always subject to change based on new evidence. And step 3, have them build their own models to solve real problems. And let me be totally clear here. Having students engage in the engineering practice of designing models isn't just some fun extra credit fluff. It directly fulfills the scientific and engineering practices, or SEPs, required in the 2024 TEKS. By designing and revising models, you are actively training them to engage in vital scientific methodologies. As we wrap up this explainer, I want to leave you with a real challenge. How are you going to incorporate this tentative, ever-evolving nature of scientific models into your very next lesson? Seriously, try setting up a great model debate. Force your students to break their models, revise them with new evidence, and watch their understanding absolutely soar. Thanks for joining me on this explainer, and keep cultivating that curiosity.